When we're considering energy and how energy changes or moves around in a chemical reaction, even though energy and chemistry are, it's a very complex field, there's really only two options. There's only two possibilities for the changes in energy when a chemical reaction occurs. Either the chemical reaction gives off heat, or the chemical reaction absorbs heat. Those are really the only two options. I guess technically maybe you could find some chemical reaction somewhere where there's no overall change, because there's exceptions to pretty much every rule in chemistry. But the vast majority of the time, and all the situations we are going to consider, those are the two things that are possible. Either it gives off heat or it absorbs heat. The chemical reaction does. If the chemical reaction is releasing heat, we would call that an exothermic reaction. So what's happening there is we have our reactant molecules. They undergo the chemical reaction, and the products that are made are at a lower energy than the reactants were. They have a lower chemical potential energy. Now, this difference between the reactants and the products can't just be destroyed. Again, this is the similar to the conservation of mass that we had two videos ago. There is the conservation of energy as well. You can't create or destroy energy in the same way that you can't create or destroy mass. And so if the reactant molecules were up here and the product molecules are down here, this energy difference has to go somewhere. And where it goes is it's released to the surroundings. So that difference in energy is released usually in the form of heat. Now, it can also be released in other ways, so you could give off light, for example. If it is giving off light, that it's also usually giving off heat as well. It's not just one or the other, it can be a mixture. We're just going to consider heat just to keep things simple for now. So it's going to release this energy in the form of heat, which is going to make this reaction feel hot to us, because we are part of the surroundings for the reaction. Or at least I sure hope so. I sure hope that you are not a part of the chemical reaction. That would be bad. We want to be observing the reaction as part of the surroundings. And so when the reactants release that heat, if we were to touch the beaker, for example, that this reaction was happening in, it would feel hot, because we were feeling the release of that energy. And it is a little bit counterintuitive here, because you're thinking, well, wait a second, but it's going to a lower energy. Why would it be hot if it's going to a lower energy? And so you kind of have to move yourself out of the mindset that if the molecules are going to a certain chemical potential energy, that chemical potential energy is going to directly correlate to the thermal energy. So what we're really doing is we're converting chemical potential energy, which is what this is measuring here, we're converting that into thermal energy for the surrounding molecules. So the release of energy here gets converted into a different kind of energy that is given to different molecules. So it is a little bit confusing to think about that the overall energy of our system decreases, but then again, we're not feeling the heat of the system there. We're feeling the heat of the surroundings. The surroundings are getting heated up. The opposite is true if our chemical reaction absorbs heat. That is what we call an endothermic reaction. So if our reactants start off lower and they have to go up in chemical energy, what that means is they have to suck the heat out of the surroundings. They suck energy out of the surroundings, which again is usually in the form of heat. So they suck the heat out of the surroundings so that they're able to make these products that are at a higher chemical potential energy. And so this is going to feel cold to us, because again, we are part of the surroundings. And so it would be sucking the heat out of the beaker that's holding the reaction, and so when we touch the beaker, we can feel that the beaker is now cold because it had thermal energy sucked out of it. Alright, so that is endothermic and exothermic reactions. Those are really the only two options that we have when it comes to energy and reactions. Okay, so let's talk a little bit more about temperature. We briefly discussed this in one of the earlier chapters, last chapter, chapter 2. What we didn't really discuss was what exactly the temperature was measuring. I think I might have just briefly mentioned it, but we're going to discuss it a little bit more in depth now. So the temperature of an object is directly related to the kinetic energy of its molecules. So the more kinetic energy, the more thermal energy something has, the hotter it is. And then vice versa, the cooler it is, the less kinetic energy it has. So we use the Fahrenheit temperature scale here in the US, but it is really inconvenient to use that for scientific purposes. Like, it does not work terribly well. You have a lot more work to do. It can work, and some people do make it work, but why do more work when you can do less? So we're going to be using the Celsius and Kelvin temperature scales, and mainly Celsius for this section here. So again, just to remind you of the differences between these, in Fahrenheit, water freezes at 32, but it freezes at 0 in Celsius. It boils at 212 Fahrenheit and 100 in Celsius. This is one of the reasons why Celsius is so nice for scientists, is because we have this nice 0 and 100 degree freezing and boiling points for water. Kelvin is just the same thing as Celsius, but with 273 added onto it. Technically 273.15, but most people just leave off the 0.15. And it's just one other thing to remind you of here. Remember that a degree in Fahrenheit is not the same as a degree in Celsius or Kelvin. The degree size is actually larger in Celsius. So it takes 180 degrees to go from the freezing point of water to the boiling point in Fahrenheit, but it only takes 100 degrees Celsius to do that. So a degree in Celsius or Kelvin is larger. Alright, so with that little reminder out of the way, let's talk about actually measuring the temperature of a sample, or more specifically, measuring how the temperature changes due to a chemical reaction. So when we're monitoring a chemical reaction, or even if it's not a chemical reaction, maybe it's just we have a piece of metal or something and we're just heating it up. Regardless of how the heat is being moved around, whether it's chemical reaction or something else, the movement of that heat, either going into a sample or going out of the sample, is going to affect the temperature of the sample. The tricky thing is, though, if you put a certain amount of heat into one material, you will get a certain change in temperature. So maybe you put some energy into one sample and the temperature goes up that much. But if you put the exact same amount of energy into a different sample, it might get this change in energy, or in a temperature. You put the exact same amount of energy in both samples, but because the material is different, you get different changes in temperature. And this is true for every material. Every material is going to have a slightly different, what we call heat capacity, or specific heat capacity. And what this heat capacity measures is how much energy does it take to increase the temperature of the material. Now, the plain old heat capacity, which is this here, this is not terribly useful because this is defined for an object. It's used for a specific object. So if you had a beaker that you were using for a reaction, you could define the heat capacity for that beaker. which might be useful, if that's the only beaker you're ever going to use, but chances are you're going to be using a lot of other stuff, and so you would have to define a heat capacity for every single individual thing that you ever used, which is possible. You could do it, but man, it'd be a pain in the neck. And so instead, what we've done is we use what we call the specific heat capacity. And the main difference here is that instead of defining a heat capacity for an object, the specific heat capacity defines the heat capacity for a substance. So instead of measuring the heat capacity of a beaker, you could instead say, I know the specific heat capacity of the glass that is used to make these beakers. And so then at that point, if you know the specific heat capacity of the material, you can just take that number and use it on any beaker that you have in the lab, just as long as you know how big the beaker is, because it does matter how much stuff is in the sample. But this is a much more useful term, the specific heat capacity, than just the regular heat capacity. There is a third kind of heat capacity here that I'm just going to very briefly mention because we're not going to use it from this point forward, but some people do prefer to use the molar heat capacity, which measures the heat capacity of a mole of a substance, but we haven't even talked about moles yet, so we are just going to ignore this one for now. But I just want to make you aware that it is out there, and so you might see it if you take another chemistry type class somewhere else and they start talking about the molar heat capacity. I wanted you to at least be aware that it exists out there. We'll talk about moles in a couple chapters, but for now let's focus on that second one, the specific heat capacity. So even though you've probably never really thought about it too much, you kind of intuitively understand that there is a difference between specific heat capacities for different materials. If you've ever been in a pool in the summer where somebody just recently put the pool up, so maybe you have one of those semi-inflatable, like it's not like a little kiddie pool, but you essentially inflate the top rim and then you fill it up with water. If you've been in one of those pools before and somebody had just filled the pool up with water earlier in the day, which it takes a long time to fill those up, but somebody filled it up with water just recently, if you jump into that pool, it's going to be really cold. Because the water is stored underground, or at least it comes from underground. It's stored in different places, but the water that comes out of the faucet is not terribly warm. It's quite cold, actually. And so if you just fill up the pool and immediately jump in, it's going to be pretty cold. And in fact, it takes a long time for that pool to warm up to the air temperature, or close to it anyway. And the reason for this is because water actually has a very high specific heat capacity. It takes a lot of energy to heat or cool water. So it takes a lot of heat a lot of energy to heat it up, and if you want to cool it down, you have to suck a lot of energy out of it. The opposite of this would be something like a piece of metal. So if you've ever stepped on a piece of metal that was sitting in the sun, especially if it was sitting in the sun in the summer, where the air was already hot, and then it was sitting in the sunlight, you'll burn your foot doing that, because metals tend to have very low specific heat capacities. It's very easy to heat them up. It doesn't take very much energy to increase their temperature by quite a bit. And so you can take a piece of metal, drop it in the sunlight, come back 10, 20 minutes later, and it'll be hot enough to burn you. It'll be very hot, depending on what the metal is, because there is some variation from one metal to another. But sheet metal like that can be very, very hot if it's sitting out in the sun. Whereas you could have a glass of water sitting right next to it, and it would still be nice and cool. again, just because of the difference in the specific heat capacity. This, by the way, is why there's such a dramatic difference in the, or one of the reasons anyway, why there's such a dramatic difference between San Francisco and Sacramento in terms of their weather, especially their temperature. Because San Francisco is almost an island, really. It has the ocean on one side, it has the bay on the other side, and then there's even water kind of here. It's not quite as much water there, but it's essentially surrounded by water. And that water kind of acts like a buffer where it soaks up heat when it's hotter, which keeps the air cooler, and then when it starts to get cooler, because it had soaked up heat before, it starts to release that heat back into the atmosphere. And so it keeps San Francisco relatively temperate, while Sacramento, which is not that far away, it's just inland from San Francisco, will have very different weather. It's not bad weather by any means, but it is very different than San Francisco. All right, and I'd encourage you to check up on this this checkpoint here, 3.5 in the book, to take a look at that. Oh yeah, so yeah, you can see here San Francisco. Lots of water, lots of water. It's not quite an island, but it's pretty much surrounded by water, and that's what keeps it nice and cool. Whereas Sacramento, not all that much farther away, but because it's not surrounded by water, its weather is very different. All right. So I know this is going to be a slightly longer video here, but it's good to go ahead and get it all in one go here rather than having it split up. So this is the equation that we're going to use to quantify how much the temperature will change based on the heat that is put into a system or pulled out of a system, or vice versa. Maybe we know how much the temperature changes, and we can find the amount of heat that either went into or out of our system. So what this equation is saying is the heat, which we represent as Q, is equal to the mass, which is in grams, times the specific heat capacity, which has units of, let's see, that would be grams per degree C, I believe. Joules. Sorry, joules per gram. Sorry, joules per gram degree C. That's right. And then the temperature change is just degrees C, are the units on that. And anytime you have a delta T like this, or a delta anything, whether it's temperature or not, it is always the final minus the initial. So it's the final temperature minus the initial temperature. So let's look at an example here. Actually, I think I'd already mentioned this on the previous one. Yeah, so joules per gram degree C, T2 minus T1, which is just another way of saying final minus initial. So let's do an example here. So this is example 3.1. It says gallium is a solid metal at room temperature but melts at 29.9 degrees C. If you hold gallium in your hand, it melts from your body heat. How much heat must 2.5 grams of gallium absorb from your hand to raise its temperature from 25 to 29.9 degrees C? And it gives you the specific heat capacity there. So why don't you go ahead and try to solve this on your own. So read through the question again. Make sure you know what it's asking you to find. You should have a good idea of what equation to use, since we only have one. And try to solve this question. So go ahead and pause the video now and try to work that out. All right. Hopefully you gave that a shot. The question is asking us to find Q. It says here how much heat must that much mass of gallium take to raise that by that temperature. So we're trying to find Q. That's what we're trying to find. So we're told that we have a mass of 2.5 grams. We are given the specific heat in the problem. And we are given the two temperatures. So again, we know it's final minus initial. So we know the final temperature was 29.9. The initial temperature was 25. Both of those were degrees C. And so if I go ahead and do that math, what I get is Q is, and I'll put it down here, Q is 4.557 joules. So not a whole lot of energy, but gallium melts very easily. I actually held some gallium once. It's pretty weird, actually, to take a metal and then hold it in your hand and it melts in your hand. But it does not take very much energy to do that. So that number makes sense to me. All right, let's look at another example here. A chemistry student finds a shiny rock that she suspects is gold. She weighs the rock on a balance and obtains the mass. It's 14.3 grams. She then finds that the temperature of the rock rises from 25 to 52 degrees C upon absorption of 174 joules of heat. Find the heat capacity of the rock and determine whether the value is consistent with the heat capacity of gold. And then it gives us the heat capacity there. So again, I'd like you all to try to work this out on your own before I work it out for you on the screen. So if you would, pause the video and see if you can solve this on your own. Okay, so in this one, we're not trying to find Q. We're trying to find CS. We're trying to find the specific heat. And so I'm going to go ahead and do the algebra first. If I divide both sides by m and delta t, what I end up with is this. The specific heat is equal to Q divided by m delta t. And all of these I know. So if I go ahead and plug in what I know, I was told that it absorbs 174 joules of heat. So that'll be positive 174 joules. I'm told the mass is 14.3 grams. And I'm told that it goes from 25 to 52. And I remember that it is always final minus initial. So it's going to be 52 minus 25. So if I go ahead and plug all that in, I get CS is 0.451, essentially, joules per gram degrees C. Did the chemistry student strike it rich? No. Unfortunately, she did not. She probably has some pyrite that is too high of a specific heat capacity to be gold. If it was really close, if it was like 0.13 something, you might be able to say, oh, it might just have some impurities in there, and that's why its specific heat capacity is off a little bit. But being nearly 4 times higher than it should be, it's definitely not gold. All right. That is the end of this chapter. I know this video was a little bit long, but like I said, I think it's good to not break up a topic like that if we can avoid it. So in the next chapter, we will continue on. And if you have any questions about what was in this chapter, feel free to email, or we can chat the next time we get together.